In this presentation, I want to ask why it is that we collect normative reference data in clinical gait analysis. In the old days, we were virtually told that different laboratories were going to collect data in different ways, and that the only way we could make sensible clinical interpretations was to compare our clinical interpretation with our normative data ranges collected in the same laboratory. We can see this if we look at the data represented in different textbooks at the moment. If we look at the most recent Gillette book, we see that this normative data range for knee flexion is presented. And if we look at my textbook, you'll find that an extremely similar knee flexion extension range is published. However, if we look at another textbook, you'll see that in this normative range is showing considerably more extension of the knee in late single support. And if we look at yet another data set, we'll find that this suggests that there is more extension at initial contact, but much more flexion than in the other data in late single support. The data is quite clearly similar in its broad patterns, but quite different in its detail. Does it matter? Well, at one level, if we're all comparing our data against our own normative data, then no, it doesn't. But can you think of any other field of measurement that tolerates different equipment making different measurements when they're measuring the same thing? Imagine going into a bar and asking for a pint of beer, and the barman brings a glass that's much smaller than you're used to, and you complain and say, "Excuse me, that's not a pint of beer," and he turns around and says, "Yes, it is, sir, it's the way we serve beer in this pub, and it doesn't matter because we serve it in the same size glass to all our customers, except we don't have very many customers anymore." So I'd like to suggest that the reason we collect normative data should not be to hide away the fact that other measurements are different to anybody else's. It should be to compare with other people's data so we can calibrate our measurement technique to ensure that we're all making the same measurements. And in this presentation, I want to put forward a framework for comparison of different data sets. So let's take these two different data sets. They're characterized by the mean trace in the middle and the standard deviation bands on either side of it. And let's talk first about those standard deviation bands. They represent the interperson variability within the normal sample that we've got, but also the measurement variability of our techniques. Which means that, broadly speaking, the smaller the standard deviation, the more consistent are the measurements. The standard deviation tends to be fairly constant across the gait cycle, so the average standard deviation is a good summary statistic. And if we calculate that for these two different laboratories, you'll see that there is evidence that the blue laboratory is making more consistent measurements than the red laboratory. If we overlay the data, however, you'll see that there are also differences between the mean traces. The differences between the mean traces are suggesting that there are systematic differences between how the two gait analysis services make measurements. Those of you who've heard me explain how the gait profile score is derived won't be at all surprised to hear that I'm suggesting that we base this comparison on the area between the two curves. Except I want to be a little bit more subtle here, because what each individual service should really be interested in is not how it compares with another service, but how it compares with the population mean. And the best estimate we have of the population mean, assuming that we don't think one service is better at making measurements than the other, is actually the mean of the two samples. So you can see from this that the difference between the measurements overestimates the error. And I'm going to suggest that we use the difference from the mean as the fundamental measurement. The other thing that's very useful about this technique is it allows us to compare more than two labs sensibly without getting thrown into a series of pairwise comparisons that can get quite messy. As with the GPS, I'm going to suggest that we actually calculate the root mean square difference between the traces, which can be broadly visualized as the area between the graphs. So by way of comparison, I've taken data sets from two of the most highly respected clinical services in the world. They've got very similar age ranges for their patients, and if you look at the two laboratories' anthropometric data, you'll see that the body mass, height and leg length of the two laboratories is extremely similar as well. There are some differences in walking speed, suggesting that the children in Melbourne are walking about 10% faster than those at Gillette. If we just overplot the data and make a qualitative comparison, you can see that there are small differences in pelvic rotation, hip flexion and knee flexion, and all of these are consistent with the small difference in walking speed. There are some other differences in ankle dorsiflexion and foot progression, and these are largely attributable to slightly different techniques in toe marker placement. Melbourne uses a much more proximal toe marker to Gillette. And there are differences in the hip rotation graph, suggesting that one laboratory measures hip rotation about 6 degrees more internal than the other laboratory. We can look at the quantitative measures, first of all looking at the difference in the average standard deviation, and you'll see that for most of the measurements this difference is very small, but there is evidence from ankle dorsiflexion and hip rotation that the one centre is making measurements that are more consistent than the other centre. If we look at the root mean square differences from the mean, again, you'll see that, broadly speaking, there are very similar measures between the two laboratories, but you'll see that there are some differences in hip rotation and foot progression, where the magnitude of the differences is starting to get a little concerning. We can extend the exact same analysis to our kinetic data, and if we look broadly at the data, we'll see there is, generally speaking, quite good agreement, and this is encapsulated in the quantitative data, albeit in units that we don't relate to quite as naturally as the degrees in which we measure the kinematic data. Interestingly, however, if we look in detail at the comparison, you'll find that there are systematic differences in the moment data which are larger than we might expect. For example, in this graph you can see that one of the laboratories is measuring about twice as much hip flexor moment in late stance as the other laboratory. And it's our feeling that this is a factor that needs to be investigated, but we would not have been alert to a potential problem in one of the systems if we hadn't compared this database in the first place. So, by way of discussion, we've described a graphical and quantitative method for comparing normative data sets for different gait analysis services. We've illustrated this with comparison of two data sets, but the method can be extended to as many data sets as we want. Generally, the data shows good agreement between two highly respected centres, particularly in relation to the kinematic data. And the analysis allows differences to be highlighted and gives pointers to how agreement can be improved. We're hoping that we'll submit this to Gait and Posture, and if it's accepted, we will lodge the means and standard deviations of the two centres' normative databases as an electronic appendix, which will allow any centre to compare its measurements against these benchmarks. Thank you very much for listening.